Good afternoon, everyone. Hope you guys are doing very well. In this lecture, we're going to be discussing about very famous Black-Scholes option pricing model. Okay, um, this is a fantastic work, and due to that work, Black and Scholes they got Nobel Prize in economics. Nevertheless, the concept behind these equations they emerged from mathematical physics, and basically they applied the physics concepts for economic problem, okay, and that eventually led um, to to a great work what they did, and they got the Nobel Prize. Nevertheless, since the concept comes from physics where the continuity is there, okay, we are in a continuum. Here in finance, that may not directly be the case where you're buying or you're selling some assets in a discrete time. Okay, so let's not go into detail of the continuous time or discrete time. Let's try to understand at a conceptual level what Black-Scholes equation says in continuous time. So the question came that how do we value an option? Okay. So before saying that, let's talk about our function, which will give us the value of an option, and what would be a form. Let's for a simplistic way, let's say our value of an option v. It takes different arguments, that function. Out of those, S and T are some variables. Sigma and mu are parameters associated with asset price. E and T are parameters associated with the contract, okay, and R parameters associated with the currency in which your asset is being traded. Okay, now parameters associated with the contract, you may think about strike price of an option and maturity date. Okay, simplicity, very simple. And S and T, you may think about spot price at T at what time, what is the price, okay, for that asset. And sigma and mu, they gives you the parameter which are associated with the volatility and the drift of the asset. Now, if we have a portfolio, okay, so let's say we have a portfolio, and so what will be the value of the portfolio? Okay, we can represent by this equation, pi equal to V minus delta S. Now, what is the delta? So think about we have this portfolio of one asset in long position, okay, and then we want to have for very short duration, okay, some position delta, okay. So pi, as we said, value of the portfolio, V is nothing but your option value, and short asset position, okay. So delta you think of quantity, okay, and you multiply it simply by the price, but for very short duration, okay. So that equation will give us the value of the portfolio. Now it's very intuitive to ask what will be the little difference in our value of portfolio if there is a small change, okay. So in physics or mathematics, we say, okay, let's take a derivative, okay. Let's take in calculus, we study that, let's take a derivative. So if we take the derivative of this equation 1, and so we can find out the change in portfolio value from time t to dt, right? And that we can give us by this equation, okay. So d pi equal to d of v minus delta d of s, okay. Notice here d of s and s we don't know the future price. Okay. Let's call it equation 2. Now, assuming that we are following a random walk, And that is being said in many times in finance, that the stock prices, they follow a random walk. What it means that what we are trying to do is that we are trying to say that there is a random process, a linear process, or Brownian motion process, okay, which follows a Brownian motion. And our asset price, or our asset, that is following log random log normal random walk, okay, means that it will have a normal distribution in probabilistic or statistical term. So Brownian motion can give us the equation for change in stock price, okay, ds. Now always remember that the Brownian motion, when we are talking, it is saying that it is in continuum. The process should never stop. It's like a shark. It should always have to swim, otherwise it will die. So in the same way, process always has that process which follows the Brownian motion, that always have to be in motion, as simple as that. So what it means that whatever we are discussing here, whatever these equations are discussing, we are limiting them and we are assuming that our process is continuous, okay? It never stops. It's in continuum, okay? So let's call it equation 3. So as you see, we have these 3 important equations, okay, to start with. Very basic. There's nothing complicated here. Okay, good. Now, from the Ito's lemma, those who are not familiar with Ito's lemma, you may check the textbook, but here for simplicity, we are just gonna use that Ito's equation, okay. Ito's equation, we just gonna use that, and we know that the change in the value, okay, the dV, small change, and in calculus we represent it by a derivative, okay, simply. So small change, that will be represented by this equation, that partial derivative with respect to time dt plus partial derivative of v with respect to s ds. Notice that here v, the value, it is the value function has s and t, 2 variables, okay. So now if we're gonna determine the dv, we have to take a partial derivative with respect to s and as well as with respect to t, okay. And we already said that the value of the option, okay, an option is for our some asset, and asset is moving, you know, randomly and following Brownian motion, basically the random behavior, and we can write a derivative change in the value of v by the Ito's equation. Let's call it equation number 4. Okay. So as you can see here that we got dv, we got ds. So what about d pi, the change in portfolio value from t to t plus dt? So we can simply, put the values of dv and ds in the equation 2, and we get this equation number 5. Now, interesting thing to note here that except wherever the ds is coming, okay, this is a term which gives us the randomness. These terms, wherever ds is coming, because we don't know what's going to happen to the stock price or asset price in future, and that is causing the randomness here. Okay, we know the time, okay, so we can determine the time, okay, that we are controlling, okay, 1 day, 2 day, 1 minute, 2 minutes, okay, at what time is time we have that value. So these terms which are associated with D and S, they are cause of randomness. And we can rearrange this equation for that term, and as so simply delta V over delta S minus capital delta and ds, that is our randomness in the whole equation number 5. Now think about how we can reduce this randomness. Okay, so for per se purposes, if we say that delta equal to delta V over delta S, then whole randomness term becomes 0. Okay, or in other words, we call that thing delta hedging. Okay, and delta hedging is nothing but the reduction in the randomness. So we are trying to reduce the randomness, okay, in our equation. And so what we can do, like say if the delta V over delta S is capital delta, the whole randomness is 0, and we make use of concept of delta hedging. Okay, now another concept, let's say another thing, you may think of, okay, I don't want to buy the option, right? But instead I want to invest my money into an interest bearing account in a bank. Okay, now if I invest the money in the bank, it's a risk free, I'm not taking any risk, and I'm gonna get return at some rate, interest rate. Okay, so that interest rate, and how much I'm gonna get a change if I put the money in a safe interest bearing account is R by dt. Good. Let's call it equation 7. In the equation 6, what we just simply made use of concept of delta hedging, okay, and we equated put the delta equal to delta V over delta S and put in the equation number 5. Okay, so we get d pi equal to this. We just get rid of this random term, made use of hedging concept. So due to the hedging, we got equation number 6, and due to arbitrage concept, no arbitrage, we got equation number 6. Okay. Concept of no arbitrage, that okay, if we have money, instead of buying an option, we just put in a bank, and we just reap off the benefit for equivalent cash in a risk-free interest-bearing account. So we got these two equations, 6 and 7, and the change in our value of the portfolio d pi from both equation number 6 and 7, we can equate it. Very simple. There is nothing complicated here. So we got 3 equations. Original first equation, the value of our portfolio. 6th equation, change in the value of portfolio, making use of delta hedging, and equation 7, making use of no arbitrage principle, that if we put our money in the bank. Okay. So can we simplify these equations? Well, it's very simple. We just, what we did here, in the equation 7, we put the pi value. Okay, in the equation 7, we put the pi value. So this right hand side would become R V minus and S dV over ds. Okay, now remember the delta we are already saying we are using the the delta hedging principle. So delta is equal to delta V over delta S. So V minus delta V over delta S into S and dt simply, and left side becomes the equation number 6. Very simple. And we rearrange the terms, and we finally arrive at this equation, and this equation is linear parabolic differential equation. Okay, and this equation is known, equation number 8 is known as Black-Scholes equation. It's a very simple equation and a very simple way of understanding the concept of Black-Scholes model. Okay. However, there are certain assumptions. We have to notice those assumptions, or we have to keep in mind those assumptions. If we say just, okay, we got the holy grail of option pricing, okay, which doesn't include mu or sigma, which are related to volatility. But no, see, there are certain assumptions, and if we don't pay attention to assumptions, there is a danger that we will abuse this equation, and we might end up losing billions of dollars. What similar thing what happened to the LPCM company, long-term capital management company. They were just blindly following, well, I shouldn't say blindly, but they overlooked many things, and they were just trusting on this basic mathematical equation number 8, Black-Scholes equation. Oh, we got the holy grail. Well, the equation is fairly good. It's a fantastic equation, but if we use those assumptions, always remember the equation came from the physics, and in physics everything in continuum, and we know things how they are, like we precisely know the behavior. But here the assumption is that the volatility is constant. Well, that cannot be. Okay. So first assumption is the process is a log normal random process. Okay. So all our assets, they are following a Brownian motion. Okay, asset prices, more precisely. And there is no transaction cost, no taxes. That is an assumption. And we don't get any dividends. But hold on a second, there are new models people have developed where they modified the basic base level Black-Scholes equation, which includes dividends. But original equation, that assumption was there, that no dividends are there. No arbitrage opportunities. Delta hedging is done continuously. As we already said, that delta hedging, we are making use of the delta hedging principle. And continuously means that we are in a efficient market. Okay, that is the most important condition here. It's very simple that if your process is not continuous, okay, and if you try to use this equation, no, it's whatever result is going to give, it's garbage. And notice here, it's not the value of the option you are getting in terms of change. This equation is not giving you the actual value, it is only giving you the change. And if you solve this partial differential equation, then you can get the value of the option. Now, how to solve? There are, you have to put different conditions, you have to put boundary conditions, and there are numerical packages to solve that equation. How to solve this equation, that's beyond the scope of this lecture. I might be discussing in some other lecture. So that's important. Delta hedging need to be done continuously. That in efficient markets, people are all the time buying and selling assets. Activity never stops. And the risk-free rate, what we assumed, okay, then that, okay, if we put money into the bank, or let's say we buy the government bonds, for example, we know in advance that what it's gonna be, okay. So there are a bunch of assumptions behind this equation. Nevertheless, it's a very fantastic equation. Now let's talk about currencies, how we can modify these equations for currency options. Well, it's very simple. In terms of currency, let's say we are holding the currency, or we decide to buy, we are sitting in United States and we decide to buy euro. So RF is nothing but, so we subtract the risk-free rate for the euro, okay, interest rate, foreign rate of interest, from our rate, our base currency rate, and we get this equation. Let's call it equation number 9. So if you see the difference between equation number 8 and equation number 9, it's same, except instead of R we have R minus RF, foreign rate of interest, right? We can extend this equation for commodity pricing. So in terms of commodity, we need to think about that we are not holding the commodity, so we have to pay taxes, or we have to pay, it's a form of tax, or some sort of we have to spend money or give the commission to the person or to the company who is holding that commodity for us, okay. So we add the Q is nothing but the fraction of the value of the commodity that goes towards paying the cost of carry. So the cost of carry we add with R, and the rest of the equation is same, okay. So let's call it equation 10 if you want to use Black-Scholes for commodity pricing, okay. Well, nothing, no bread no lunches are free. That's a sort of saying here in the world. So same way, if somebody is holding the commodity for us, we have to pay. And how are we gonna pay? We're gonna pay from the from our asset, okay, for the value of the commodity, that or some fraction of the value of the commodity, which will go, or you may think of which will go towards paying the cost of carry in any way you can think of. We can extend the Black-Scholes for future contracts as well, okay. So what it is in the future contracts? Well, futures are simply, these are contracts which are, you know, for a future date, okay. So it's very simple. The future contract, we have F as a future price, okay. So instead of you know, using the V as a value of the option, we want to know what gonna be the future price. So same equation, instead of V we just use the F, and we have no more R into V, because it is the future price. It's not really anything you are holding, it's coming in future, okay. Let's call it equation number 11. How about options on future? Well, future are again derivatives, and now very interesting. How about derivatives on derivative? It's like bomb on atom bomb, okay. So but yes, we can mathematically represent options on these futures. It's very simple. Instead of capital V, we are now using another variable called nu, okay. And nu is the value of that option on future, okay. And how the future price and the spot price are related together by this equation, okay. E to the power R TF minus T and spot prices, all right. And we have just, you know, used nu instead of V, in original Black-Scholes equation, and we got the options on futures now instead of options on stock. Okay, so far we were saying it's very similar analogy. When we were using capital V, we were using options on stock price, as was the stock price. Now if we are using options on future, then we're gonna use, what would be the future price. Okay, and the future price and spot price are linked with this equation A. Okay, so guys, I hope you have learned and you have enjoyed this discussion on basic Black-Scholes option pricing equation. Thank you for liking the videos on YouTube. Thank you for subscribing and your wonderful suggestions, feedback. And always remember before we end this session that derivatives are atom bombs. Beware of that. These are financial atom bombs, these derivatives. The collapse of Lehman Brothers and the banking, let me put it that way, economic collapse in 2008 is very much related to these derivatives, that people were trading the credit default swaps and a bunch of complex financial derivatives, and they were not careful, so it blew them up. So always remember, derivatives are atom bombs in finance. Thank you and have a wonderful day.